Although we have proven that masked AES was secure under first-order DPA attack, we found people claim in their documents that their methods of second-order DPA attack could break masked AES. Also, they just described them in theory without sharing their source code. Despite this fact, we are also trying to further verify security of our system, and we decide to play the role of attacker once again. To conduct a second-order attack which requires at least 2 points a time for processing, we need two things. First, the power trace. We need to locate exactly where this one more point on trace should be, and second, the method to process. We need to design how exactly we process these 2 points on trace to make them have correlation with our intermediate values. As the aim is still to correlate something with intermediate values, the theory should be the same as first-order DPA attack. The only difference is 2 points on power trace should be able to be processed to cancel out the mask. Let us take a look at the power trace. Despite the fact we were the one who implement the system and we know approximately when mask was generated, while we put ourselves in attacker's shoes, we will find out that it is nearly impossible to guess out where the mask was generated. The only way the attacker could do was to guess with automatic algorithm point by point, and this could possibly take thousands more times effort. Despite this fact, we are still considering this small potential danger and verifying it. In our power trace, the point when mask was generated was marked out by 2 ranges of no operation which nearly consume no power. With this, we consume much less time to guess. We could see peaks occurring every 14 points, and they represents rising edges of clocks. We could know that mask could be written to memory at any one of these peaks. As mentioned, we know the first round was easiest to attack, the same goes in second order attack, as it is still easier to locate. I marked out the time when first byte was being processed here with no operation, and we could see that in one of these peaks, the masked intermediate value after first add round key could be written to memory at any of these peaks. With these information, we have multiple points to process, and now, the processing method. According to results we have, Hamming weight of a value have the most correlation with the actual power trace. Hamming weight of one value x or another equals Hamming weight of this value minus Hamming weight of the other. With these, we draw an astonished conclusion: Hamming weight of one value x or another correlates to one power point minus another. With mask m in, the value after add round key should be the supposed value with mask m in. The Hamming weight of this value x or m in is exactly Hamming weight of plain text x or key. With only one variable to guess, which is the key, the attacker could possibly review the secret key. We could see that this will be possible when we use these 2 points, the point when mask was generated, and the point value after add round key was written to memory. The one with the most correlation should be the correct secret key. With this method, we really managed to attack the correct secret key for the first byte, and here are the correlations for correct key for the first byte. We could see from this figure that the correlation of second-order DPA attack was much smaller than that of first-order DPA attack. The reason why we are not trying other bytes was because we require the power trace to be zoomed in for a certain resolution, or otherwise, it is hard for our scope to sample point mask was generated with the point add round key occur at the same time. With this experiment, we could prove that despite difficulties to locate the points of events, the attacker could threaten the security of smart cards running masked AES with second-order DPA attack.